Um, so you guys are working on the balls sketch. Hopefully get that in by tonight and then start on the next assignment. The next assignment is somewhat open, or it can be as open as you would like it to be, I suppose. So let's go to the syllabus here. So we're in our last week. So the first part of the next assignment is you could do a Conway's Game of Life, which is what I plan to talk about today, at least a little bit. Or you can find a sketch online and modify it in some significant way. Or you can just create one of your own. I'm going to leave it to you guys to define words like that and words like this. But, you know, it's got to be more than slapping a couple of rectangles on a canvas and walking away. Okay, and it's going to be fairly subjective, but I want to see something interesting. So keep that in mind. Along those lines, someone, I think it was Lauren, who's not here at the moment, asked if I could put these things online, and I did go through and put them online, but I want to give everybody. If you want yours removed, I have no problem removing it. But if you go to the examples directory and click on homework 9, these are the ungraded sketches. So there's no grade information that's floating around in there. But if I click on one of, like Jason's, and then go in here, it'll pull up the sketch. So you can browse through everybody's sketch. Some of them, were a little bit not quite right. Like Kendall's first one works, but her second one, there's something wrong with it, and I didn't bother to figure out what was wrong with it. So, like, for some reason, the image isn't popping up, even though the image is in there. So just keep that in mind as you go through. I haven't looked at every single one of them to make sure that they work. Questions about that? So if you would like yours removed, shoot me a discreet email, and I will remove it. All right. So the next homework is somewhat wide open. I've given you the option of doing the Conway game. The Conway game is really just kind of an indication of sort of the level I think that you should be shooting for in terms of its complication or its level of level of complication. I don't know. It's hard to describe what I mean, but shoot for something like at that level. Conway's is an interesting game. You'll all remember that you did the one-dimensional cellular automata in here several weeks ago now. Conway's is a kind of a two-dimensional version of cellular automata. So instead of having a row of cells and then generating the next row based on some rules, what we have is a grid of cells, and then to generate the next sequence of cells, we look at the current sequence, we apply a bunch of rules, we generate the next one, and then we put that back in place, and then we generate the next one and put it back in place. And it's just iterative like that. This was invented by John Conway several years ago. This looks like 1970 here. And Conway was into computation and that sort of stuff. And this is a popular topic of study in computation. What's interesting, if you look at Conway's rules here, let me blow this up a little bit. There's some deep sort of philosophical implications to Conway's Game of Life. So, those aren't quite the rules. Where are the rules anyway? There they are. Okay, rule 1, any live cell with fewer than 2 live neighbors dies. Any live cell with 2 or 3 live neighbors lives on. Any live cell with more than 3 live neighbors dies. Any dead cell with exactly 3 live neighbors comes to life. These seem somewhat arbitrary, and they are. They're interesting because they're interesting. It's this collection of rules that gives you the images that are on this web page and so much more. If you tweak these rules, you'll see that all the cells die out really quickly, or all the cells fill up the whole grid really quickly. So it's just, there's something about this particular set of rules that makes the simulation interesting, non-trivial. That's not to say that these are the only non-trivial rules that you can put on a two-dimensional cellular automata, but they're definitely the simplest ones. So think about those rules, and let's look at my example here. So let me get my sketch up here, and I'm going to knock this way back. Maybe make these guys, well, let's try 30 by 30. That might be too much. 30 by 30 cells, and let's knock the frame rate back to 1 second. Okay, so let me hit a pause here. Oh, come on. There we go. Okay. Really? So for whatever reason, my pause button is a little bit delayed. Let's look at some of these cells and think about what might happen in the next iteration. So here's the current iteration, and what we're trying to do is figure out, let's look at this cell. Is it going to come to life or stay dead in the next iteration? Well, we can go back and look at the rules. Can we? Any live cell with fewer than 2. Okay, so it's not a live cell, it's a dead cell. So any dead cell with exactly 3 live neighbors becomes a live cell in the next iteration. So we can look at this guy right here, this empty cell that's next to this guy, and we know that it's not going to come to life because it has 1 live neighbor. Carter?
When you say next to, are you talking about diagonal to?
I'm talking about there are 8 neighbors.
Okay.
So here's a cell, and it has 1, 2, 3 at the top, 4, 5 in the middle, and 6, 7, 8 on the bottom. Yep, diagonal and north, south, east, and west. So yes, so I look at this guy, and I ask myself, is it going to come to life? And the answer, is, of course, is no. Are there any cells that are going to come to life? This guy right here will come to life in the next iteration because it has exactly 3 live neighbors. This guy will come to life. This guy will come to life. It's kind of like playing Minesweeper. This guy will stay dead. So can we find any cells that are going to die? Well, this guy's going to die because there's only 1 live neighbor. And this guy's going to die because it has too many neighbors. So if you have 3 or more, I think, or more than 3, I think is what it was. Any live cell with more than 3 neighbors, so 4, 5, or 4 through 8 neighbors, and you're going to die. So that guy will certainly die. I'm guessing the unreliability of my pause button is not going to allow me to start and stop this thing in 1 frame. So just keep an eye on that guy. That guy's going to go away. I'll try to do it. Nope. Oh, you know what it is? It's the 1 second frame rate. So it's not looking at the pause button long enough. Come on. Yeah. Anyway. Now I'm getting too many pauses. You get the idea. This is not as interesting when you're looking at such large blocks. So let's go back and reset this guy. Come on. go back and reset this guy. And let's make the cells one by one and put no border between them. So this is going to look like a bunch of bacteria. I'm not even sure it'll show up well on the screen. Oh, and I'm still on my 1 frame per second. Let me go back and make it 10 frames per second. Looks pretty random. But if you let it run for a while, you start to see certain things emerge. Let me go here. So you see little islands of stability, and there's a little guy that just flips back and forth all the time. There's some more guys that flip back and forth all the time. And they're safe as long as nobody comes in from the outside and interferes with them. So that guy just disappeared. There's something called a glider. And you can almost always spot a glider. There's one right there. There's a glider. There's one. You would never expect such a thing to emerge from these 4 sets of rules. And so what you see is what appears from afar to be really random kind of behavior, but when you look closely at it, you see interesting structures. So let me change it a little bit more. Let's crank it. Let's make this 3 by 3, say, with 1 cell, 1 border cell, pixel, excuse me. So what I do is I start the whole simulation off. Every cell has a 50-50 chance of coming to life. So I just go through the whole cell array, and with a 50% probability, I light up a cell. And then I let the rules take over. Now you can really see some of these stable structures. So there are static structures that are stable, and there are dynamic structures that are stable. And these guys will go indefinitely as long as they're not interfered with from the outside world. There's a little glider who just exploded. Let's see if I can find a glider so that you can see it. There's a glider right there. That's what one looks like, and slightly larger. It's going to go until it hits something. And I can add a cell by clicking the mouse. And it's hard to, if I drag really slowly, they just die of loneliness. But if I go really fast, I can get some going. On the other hand, if I pick one of these stable but dynamic structures and I click, I can wreck it. If I click again, just by lighting up a cell, I change its dynamic. And then there's a stable. If I click there, here's one. I'll fill in that guy. That was kind of interesting. So my pause button will stop this, but I can still draw things if I want, and then I can start it again. I have a clear button, C, that kills everybody. I have an R button, which sort of randomizes or repopulates. And if I pause this thing and I repopulate, there's essentially a grid where there was a 50-50 chance of a cell coming to life. And if I hit R again, I just get a different random shuffling. You can see that this is a highly overpopulated screen. And as soon as I start this thing, most of these cells die. So the very next iteration is has substantially fewer live cells.
So there was 50%?
Yeah,
Live.
that's 50%. Give or take, right? Yeah. I don't know what kind of... I have to say, there's really not much value to this simulation other than just it's kind of interesting to look at and play around with. I don't know that there are any scientific applications of this kind of stuff, but again, it's kind of fun to look at. There are cellular automata rules that simulate ideal gases, for example. Let me see if I can find one on the web. Or maybe diffusion. Let's do diffusion. So you can model some diffusion systems using cellular automata, but it's a stretch. It really is. Mostly this is just an interesting philosophical curiosity. I mean, why do I say that? Well, one can imagine that this is the way that the universe works at some level, right? You have all of the fundamental particles in the universe, right? The cells, and they all interact with each other according to rules. And the rules are very simple, and the fundamental particles are very simple, and yet through the successive iterations of these things interacting, you get complicated things like trees and people and stars. And so I think that's another thing that Conway really liked to think about when he was putting together this simulation is it's really surprising that from these simple rules you get these complicated behaviors, these unexpected behaviors. You certainly can't look at the rules and expect that you could build a glider generator. But that's what this is. This is a periodic structure that spits out gliders, and it's following the same rules that are listed below. And so you can look at the laws of the universe, the laws of physics, and you look at these fundamental particles, and you can't look at them and say, oh, trees are going to come out of that and stars, but they do. So people like to think about Conway's game of life as kind of a metaphor for possibly how our own universe works with its physical laws and its fundamental particles. Okay, let's stop talking philosophically and think about implementation. So I'm going to talk a little bit about the implementation here. Again, it's not necessarily the case that you'll do this one. I've given you a lot of latitude, but it's a fun one to do. The heart of this simulation, and I'm only asking you to do a simulation that looks like this. So let me go back to the more sort of bacterial level cellular automata. This is the simplest way to do a cellular automata, a Conway's game of life, where every cell corresponds to a single pixel. So this is a 500 by 500, I think. I don't remember what it was, 500 by 500. So there are 500 by 500 little cells. And you just simply build an array that is the same size, in fact, two arrays. You get two arrays that are the same size as the canvas. And then you populate the first array randomly or however you want to do it. And then you apply the rules to copy the first array into the second array. And once you've applied the rules to every cell in the first array and get the second array, take the second array and copy it on top of the first array. And then do it again, and do it again, and do it again. And this is the iteration, and it happens at this frame rate. Let me show you the heart of where that's occurring. So the rules are applied in my function that's called update cells. And what it does is it goes through oh, this is more complicated, excuse me. Let me go down to the main loop. Okay, what it does is it goes through every cell in the array. So I from 1 to num cells, j from 1 to num cells, and it computes this thing called a neighborhood sum. In my cellular automata, a cell is living if its value is 1, and it's dead if its value is 0. So I compute this neighborhood sum by taking the values of the cells around the current cell. So maybe 1, 0, 1, 1, 0, 0, 0, 1, right? I add them up. That's going to be a number between 0 and 8, right? Because if they're all living, then that's 8, and if they're all dead, that's 0. But it can be anywhere in between. And then I apply the rules. The death rule is underpopulation or overpopulation. Then the next iteration, that cell is 0. Otherwise, the cell just lives on in its current state, either dead or alive. And then there's the life condition. If the neighborhood sum is exactly 3, then the next grid comes to life, 1. So all 4 of Conway's rules are captured in these 3 lines. When I'm done, I take the current grid and I swap it with the next grid. And in Java, that's actually really easy. In C++, you would have to have a for loop, a pair of nested for loops that would copy the next generation to the current generation. It would do the swapping. But in Java, I can just take the names of the arrays. So I take current grid, put it in temp, next grid equals current grid, current grid equals next grid, and next grid equals temp. And that effectively swaps the 2 grids. And then I do it again, and I swap the 2 grids, and I do it again. There's this bit about the middle cells, no boundary cells. What's a complication here when you're updating the cells? What do you think I'm talking about there, no boundary cells? The top row, the right column, the bottom row, the left column. Why not?
Because when you do j plus 1 or I plus 1,
you go out of bounds, right? So, in other words, the generic neighborhood for a Conway, the generic neighborhood looks like a tic-tac-toe grid, right? Here's the cell that's in question, and in order to figure out what happens to that cell in the next generation, I have to consider all of these guys. But if I'm up at the top row of the screen, so let's say I'm interested in this guy right here, and let's do another one down there. The question becomes, what do I do up here? And there are a number of things that you can do, but this is equivalent. You've seen this problem before. When did you see this problem before? Yeah, the edge pieces for the one-dimensional cellular automata had the same problem. What was the solution in that case, or what was one of the solutions? We wrapped it around. So if a cell's neighborhood poked off the left side, we just used the far right corner, the far right end, as the neighborhood. What do you think is one solution here? Use the bottom. So if these guys poke off the top, then use these guys and slap them up there. Or if it pokes off the left side, use the right side. Or if it pokes off the right side, use the left side. That's called the torus topology. Why is it called a torus? Does anybody know what a torus is? It's like a donut. It looks something like this. Like an inner tube or something? Okay. It's hard to imagine if you haven't done this too much, but if I take this flat rectangular sheet of paper and I glue the top edge to the bottom edge, that gives me a cylinder, right? Now, if I glue the left edge to the right edge, that's the same as taking this opening and attaching it to this opening, right? And that gives you a torus. So when we make this decision to let these cells act up here and let the same thing happen over here, when we make that decision, what we're doing is treating this rectangular sheet of paper like a torus. And when you go back and you look at my simulation, let's see here. Let me crank it up again. So I'm going to go with a larger cell width again, and maybe I'll knock this down to 500. I want you to pay close attention to how this thing behaves. In fact, let me clear it a little bit here, and let me draw some stuff over here. So to these cells, they don't know that they're crossing the boundary. They just think that their life is normal. Right? So you can see, these guys are sort of interacting and they're bleeding off into this left-hand side because to them, in their universe, from their perspective, that boundary's not there. And we can put a little bit of a mess up here, and we'll see it start to bleed over into... No, we can't get it to keep going. Conway does tend towards extinction, actually. It's not... If you let this go long enough, it will sort of just peter out into stable configurations. But I decided to do mine on a torus topology, and consequently, if you want to do it sort of with maximum efficiency, it gets complicated. So here's my update cells. I have the top and the bottom boundaries that I'm dealing with, the top row and the bottom row. I have the left column and the right column, but I do all of these excluding the corners, and then I do the four corners: the upper left, the upper right, the lower right, the lower left, and then I do the interior. So to get this torus topology is a lot of work, handling lots of special cases. A simpler way to do it is to just ignore everything that happened up above. You can get a perfectly good Conway going just by updating the middle cells. And I can show you that just by commenting this out. Come on. There we go. So now I'm just not even going to compute what happens on the boundaries. I'm just going to do the middle cells. Let's save this and run it. And, you you can see a little bit of weirdness around the boundary, but if you're interested in just the behavior, the stuff in the middle is not really noticing that at all.
So that entire section was just the boundary, or was there anything else you just commented out?
I commented out everything that has to do with these boundary points. So the stuff that's getting into the boundary right now is just, stuff that sort of was there by the random. Come on, let's get going here. If I get some stuff going over here, oh, see, I lit that up by accident. But the stuff, all that stuff that was blinking around the edges was there because of the random number generator at the beginning. Nothing can get in there from the inside, right? None of these cells are ever going to light up any of these cells on the boundary. See how they just kind of die when they get there? And a lot of Conway implementations just do that. Just ignore the boundary. That's perfectly a reasonable way to go. I can't remember if I asked you to implement. I can't remember if I asked you to implement torus or not. Okay, got it. Okay, let me pause here, let Andrew do his thing, and then we'll go and we'll talk about finding a sketch online. Yeah, come on up, Andrew. Do you need the computer? Okay. And what is it, like whipmail or webmail?
Yeah.
Whipmail?
Here.
Oh, I have a hole in my pocket and I keep having change falling out. It's really annoying. I had no idea the jeans that I pulled out of the drawer this morning were so crappy. Okay, you ready?
Yeah. Okay, so I'm going to be giving my presentation on Moore's Law of computing. Moore's Law was named after the current co-founder of Intel, Gordon E. Moore, in 1965. And essentially what the law is he made this observation that throughout the entire history of computer hardware, the number of transistors in integrated circuits doubles about every 2 years. And this is huge, a huge observation that he made for essentially the entire electronic industry, because it's been holding true for transistors, memory, pixels in cameras, and just a ton of different things. And for those of you who don't know, a transistor is a semiconductor device used to amplify and switch electronic signals in electrical power. So when the number of transistors can double every 2 years, it essentially means that you can make devices that much smaller because you can get the same amount of power in less area. And this is just a graph that illustrates the transistor count. And as you can see, until about 2000, 2005, new, I guess, transistor counts weren't coming out very often, but in the last 5 or 6 years there have been like 20 or 30 just bunched up right at the top up there. And it's actually, even though he made this prediction in 1965, it's still held almost exactly true, which is a little bit weird. And a lot of people have theorized that the reason it's held true so much is because a lot of major R&D companies are using it kind of as a guideline and a benchmark to shoot for when they do all their R&D. So they're telling their guys, like, okay, in 2 years we need to have this doubled, and that's something they've been shooting for. And then these aren't really as much Moore's Law, but there are just some interesting other applications that have kind of followed the same principle. And another big question is this still holding? And I couldn't find any updates newer than 2010, but in 2010 it was predicted that at the end of this year it would be slowing down from 18 months, doubling every 18 months to probably about every 3 years. And essentially the reason for that is a big reason that they can double it is they've been when they're making these transistors, they have this technology that's really advanced that they can, I guess, get down to a microscopic level to add more, and they just aren't foreseeing that will improve quite as quickly as it has been. And then one last question that's a little tangential is the Moore's Law compensator, and it's just something that I read about that essentially it was saying that if you take a computer in 2000 and you run like Microsoft Office 2000 and you try to do some task, and let's say it takes 5 seconds to do that, not very realistic, but let's say it takes 5 seconds, and then 10 years later you take Microsoft Office 2010 with the current computer in 2010, it would perform that task at the same speed, which essentially means that the stuff we're using isn't necessarily getting faster because what we're computing with is getting that much more complex. Which is, I thought that was pretty interesting. But yeah, that's essentially Moore's Law. There's not really much more to it. Any questions? Ami?
Well, I sort of see it as like, do you think there's going to be like a plateau where people mostly use their computers for word processing, and even though we can exponentially grow the power of the computers, there's going to be a need to actually replace computers as often because we don't need any more processing.
I mean, I guess I could say that theoretically you probably would see a small plateau for like Microsoft Office, but I think they're still going to continue this trend because I'm sure they're going to need it for a lot of other like supercomputers and more advanced computations that they're going to do. And I'm sure they probably said the same thing 10 years ago for what people were using Word for. I mean, who's to say? Yeah.
There's like how I feel like philosophically it's against me to say, you know, that's good enough.
There is a limit, though, when we're approaching physical limits of transistor fabrication, because now you're starting to get into quantum mechanical.
Yeah, I think it started at millimeters, and right now it's at like 10 nanometers. It's like the smallest transistor that they can.
And you certainly can't
Can
go
we-
much smaller than an atom, unless they like a quark computers or something. I don't know. Probably like radioactive. Other questions? I think Ami makes an interesting point. That's one that I've been thinking about recently, and that is rather than look at the technology that changes so quickly, look around at the technologies that have not changed very much. The MP3 format was invented in the mid 90s, early 90s, and it's still the de facto way of compressing audio. Why? Anybody have an idea of why? Why isn't there a better way of listening to music? There's no reason to have better quality, right? The limiting factor there is the human perception. And so that's an interesting way, and like I said, it's just something I've been thinking about the last couple of years. You do, Chris, get to a point where it's good enough, right? 25 frames per second, unless you want to go see The Hobbit or whatever, at 48 frames per second, it's good enough, right? So you don't see, and so these flat screens, these Blu-rays, all that sort of stuff, there's definitely a point of diminishing returns there. You're not going to see that same kind of
Moore's Law situation with HDTV, because you're still trying to feed it into a human eyeball, which is not going to change. So if it's a way of sort of partitioning technology into the stuff that is good enough, and then the stuff that's not good enough, the stuff that needs to keep getting faster. I haven't really fully thought that through, but Moore's Law is an example of that kind of progress. Does it go on forever? What are some of the things that keep driving it? I also like the fact, and you mentioned this, Andrew, that Moore's Law has been somewhat self-fulfilling, right? That companies use Moore's Law for their planning, and therefore they track Moore's Law. Big surprise. I'd like to think that market capitalism makes that kind of self-fulfilling thing less likely, and so I think Moore's Law is probably a little bit deeper than just a self-fulfilling prophecy, because if you are a semiconductor company and instead of doubling every 2 years, you're quadrupling every 2 years, presumably you're going to break into the market. It's a free market. Presumably you're going to have a better product, and so it's going to drive Moore's Law, and it's going to break Moore's Law. So, yeah, I don't know.
I mean, yeah, there were definitely, I was looking at the data set that had the numbers behind the graph, and there were definitely a couple years, like right here, where it didn't just double, it sometimes like went up tenfold.
And then
So it's not,
yeah.
I mean, it's not completely doubling, but when you average it out over this whole long time period, it's pretty accurate.
Thanks, Andrew. Alrighty. Another big philosophical, we're finishing this semester on lots of philosophical notes. Find a sketch online, download it, and get it running. And I think this really captures a lot of how we work, how humans work today. If you go to the processing website, and you go to learning, say, and let's go to topics. Come on. Now? Okay. And just click on anything. Bouncy bubbles. This has a little bit of collision detection in it, as you can see. I think what's most interesting about processing, and one of the things that really attracts me to it, is there's the source code. So you can copy this and paste it. Come on. Yeah. Oh, I still got my sketch running, I think. Remembering my Unix commands here. Paste. How do I paste here? Let's try edit. Paste. There we go. And I think it's complaining about not being in the right directory. Dang it. You get my point. So grab that thing, copy it into your processing program, and click run, and you get this. Keith Peters doesn't really care if I grab his code and do something with it. Probably if I grab his code and do something with it, I should put at the top. I got this from this website, and it's written by Keith Peters, and then I did X, Y, and Z to it. And then I post it on the web. And you can't hide your source code, right? If I go, let me go back to the examples directory here. And I go and I run Kendall Sketch. Why does it take so long? Oh, I see. Looks like we have network issues. So I go and I run Kendall Sketch. I can run Kendall Sketch. I can also, there's no way for me to be able to put it on the web and not also put the .pde file on the web. So I can always, if I can see a processing sketch and run it in the browser, I can get the source code. So it gets to be an issue of, being careful with intellectual property, right? It's okay to use somebody else's sketch in processing because everybody that writes in processing knows that there's no way to put it on the web without also putting the source code up there. So you grab the source code and you do stuff with it. But this is one of the things, it sort of gets back to the purest kind of philosophy behind science, right? How does science work? You go off in a lab, you do something, and then you publish the results. And once the results are out there, then any scientist on the planet can read that stuff and do more with it. And the only rule is really that you give credit to the person that maybe helped you get started. You cite the paper, you cite the book, or whatever. And so this is a very open and sort of an academic or a scientific process, the notion of using processing. So compare that, for example, to when I go to Gmail. I don't really get to look at the source code for Gmail and figure out how it works. It's all hidden from me. So processing is a really open kind of language, and it builds on this whole open source idea. So to that end, I'm letting you find a sketch online and do something different with it. So you can surf around various processing sites. There's the main processing site. There's also openprocessing.org, I think, which has lots of examples. And you can grab one, download it, get it working, because sometimes you cut and paste and it doesn't quite work because maybe it's pulling in some image files or something that you need to also get into the right place. You get it up and running, and then you tweak it or you modify it. And I'm okay with that. I'm also going to add, if I get a chance between now and Wednesday, I'm going to write a Mandelbrot fractal explorer in processing, and I'll put the specifications for that up here as well. And if you want to do a Mandelbrot explorer, you can do that. The Mandelbrot fractal is probably one that most of you have seen. Oh, I forgot, no internet. I wonder if there's a way to get the internet back.
It's actually fast.
Let's go, hotspot.
Sometimes it's in Google that doesn't work.
No, I have to use Bing. Like the Google itself is
Maybe it's just like the network is having issues or something. Anybody else on the Wi-Fi right now?
I'm on a hotspot and Bing can search for Google. Like anything Google related doesn't work.
Okay. So my time is up anyway. We'll talk more about this next time. Okay. See you Wednesday. Okay.
Can I ask?
Yes.
So,